All right. So what's new? We have a quiz that's going to be posted at some point today, and I'll send an email out once that goes up. And that quiz you will have until next Friday, as you hopefully know by now, the details around that. Once you start, the clock starts. You have 90 minutes. It'll be around 20 questions covering the material from this chapter, chapter 10 and chapter 9. And it will basically cover the same material as what's on the 2 assignments. So you can start it today if you want, but I'd probably recommend that you finish assignment 2 before you get going on that. What else? Assignment 2 is up, available. Haven't heard any issues with that yet, so keep going if that's what you're thinking. We might finish chapter 10 today. We don't have too much to finish up here. Question: how many people are actually like not in Wolfville? And maybe what I'll do is send an email out to so I reach everybody and not just the 6 of you that are with me right now. I'm just thinking, like, right now you folks don't have any labs except for the virtual labs, which are kind of crappy. Sam, you're not in Wolfville. I'm just thinking it'd be great for those that are here if we could take a class at some point and do a lab, get into the lab, just our class, not everybody. And if you're not here, no big deal. It's not going to be like part of your mark. Just, I'm thinking it would be valuable for you guys to have an actual in-lab experience and maybe manipulate some chemicals, given that you are in a chemistry program. And the online labs, I mean, they're not bad for what they are, but they're not really a good substitute in my mind for actually being in an actual lab. So if you're not here, that's totally okay. We will either give you the day off or give you something else. But I'm going to try. I'll have to talk with a few people and see what I can come up with. Nothing scheduled for right now, though, but just keep in mind that this might be coming up. Okay, so we have been talking about enthalpy change, where we said that enthalpy change was the heat transferred in a reaction at constant pressure. And we looked at a couple of features of delta H. We said delta H change in enthalpy is a state function, meaning it depends only on the final state and the initial states. And another name for this phenomenon is sometimes called Hess's law. And Hess's law just says that an enthalpy change is a state function, meaning if you know, it doesn't matter what path is taken to get from point A to point B. All that matters is the difference between the initial and final positions. So here we have a bit of an example. Let's say we have carbon solid, which would be graphite. And, oh, you can't see my slides. I can see that while you see my slides. There, is that better? Yeah, for some reason when I share this, sometimes it just minimizes my screen, but it's back up now. Great, thanks. Okay, so what we have here is carbon solid, which is graphite or charcoal, and it's reacting with oxygen gas to make CO2. And let's say we want to know what the delta H of reaction for this might be. And you can see it's under standard conditions. Standard conditions means that this is being done under 1 bar of pressure. You could imagine that this goes through a pathway where it first goes to carbon monoxide and then 1/2 O2. And then that then goes through another step to give us CO2. That's probably not how the reaction goes, or it's unlikely that that's what's actually happening in this reaction. Maybe it is, but if you know the delta H for that step and that step, you can just add them together to get the overall delta H. Okay, even if that's not the pathway it takes, you can use the numbers for that pathway to derive the overall delta H for that reaction, because it's a state function, because it's Hess's law. And this is actually tremendously valuable because there's lots of different delta H's we can measure for different processes, and we can kind of add them and subtract them together as we want in order to come up with a sum that gives us an overall reaction that we want to calculate. if that makes sense. So the way people decided would be the easiest thing to do here would be to use something called enthalpies of formation. And this is the enthalpy change associated with making any pure chemical, pure substance from its elements in their standard states. Standard states are just the state that element would normally be in under at 298 K and 1 bar of pressure. So take ammonia, for example. Ammonia is a gas. Its elements that form ammonia are nitrogen and hydrogen. Both of those are gases in their standard states. So you have N2 gas plus H2 gas are the elemental forms of nitrogen and hydrogen. If you react 1/2 a mole of N2 gas and 3/2 of a mole of hydrogen gas, you get 1 mole of NH3 gas. So whatever the delta H is for that reaction, right, that reaction would look like this: 1/2 N2 gas plus 3/2 H2 gas goes to 1 mole of NH3 gas. So the delta H for that reaction, we would call the delta H of formation, because we're forming ammonia from its elements. And you can see that's written right here. If this is done at 1 bar of pressure, then it gets this little standard. And generally speaking, these are measured or corrected to 298 Kelvin. And for almost, well, not almost any chemical substance, but for thousands and thousands of different chemical substances, these delta H's of formation have been measured or calculated, and you can find these in tables. And they're always in the table at 298 K, and they're under standard conditions. So this is very valuable data because we can use these enthalpies of formations, these standard enthalpies of formation, in order to calculate the delta H for any reaction, whether it's been done before or not. We can figure out, using Hess's law and enthalpy of formations, overall delta H's for any reaction. So we get a table that looks kind of like this, right? These are all the standard enthalpies of formation for a whole bunch of different substances, and there's millions and millions, over 10 million chemical substances that have been identified in the literature, characterized. We don't have delta H's of formation for all of those. We probably have, I don't know, a couple thousand, but you can see here that for the most common substances, we have most of the values that you would need. Look at something like this. We have sodium solid has a delta H of formation of 0. And when you think about that, it makes sense because sodium solid is already a pure element in its standard state. So of course, the energy required to make sodium solid is 0 from sodium solid. And you find that's true for all the zeros in here. All the zeros that you find are pure elements in their standard states. You get something like diamond, which is a pure element, but it's not 0. It's 1.9 kilojoules per mole. That means it's not in its standard state. So the standard state for carbon is graphite. Yeah, we will be using these then to figure out delta H's for other reactions, which makes these very valuable. A few other things, just notice that these numbers can sometimes be positive and sometimes be negative, meaning sometimes forming these things from their elements is exothermic and sometimes it's endothermic. Let's look at this reaction. We are going to look at the reaction. This is ethylene. Ethylene has the structure CCH, H, H, H. No, that's not ethylene. That's ethine. C, C, H, H. C2H2. And we're going to try to turn that into C6H6, which could be benzene. Like this. And we want to know what the delta H for that reaction might be. So we don't care how it's made. We don't care the process. We don't care the mechanism. We don't care how many elementary steps there are. We don't care how many transition states or intermediates or any of those things. Because delta H is a state function, all we care is where it starts and where it finishes. And what we can do is use the heats of formation, the standard enthalpies of formation, to calculate out what the delta R is going to be for this reaction. So what we do is we go to that table that we had before and we look up C2H2. We look up acetylene, ethylene, not ethylene, acetylene or ethine. And we find it in the table, and it says it has a delta H of formation of 226.7 kilojoules per mole. And we do the same thing for the product, which is benzene, which is 82.9 kilojoules per mole. So then all we have to do is we add up the sum, we find the sum of the enthalpies of formation of the products and subtract from that the sum of the enthalpies of formation of the reactants. So you can see the equation here. The delta H of a reaction is equal just to the sum of the delta H of formation of all the products minus that same thing for all the reactants. So we just take our number. Our products are on the right. So this is our delta H of formation. It's the only single product, which goes there. And for our reactant, C2H2, we have this value, which goes here. And we have to multiply that one by 3 because there are 3 of them in the balanced equation. Then you calculate it out and you get negative 597.2 kilojoules per mole. So that's good. That tells you basically what the delta H for that reaction is going to be without having to do the reaction yourself. So if you want to figure out if a reaction is exothermic or endothermic, you want to figure out if it gives off a lot of energy or not. Let's say maybe you wanted to use it as a as a method for heating your home or something like that. You could calculate the amount of heat it's given off. But by having these tables of enthalpies of formation already there, it makes life a lot easier. So, yeah, basically what we're saying we're doing when we use heats of formation or enthalpies of formation like this, what we're basically suggesting is that we're taking our starting materials, breaking them down into their elements, and then putting those elements back together to give the product. And that's not physically what happens in any chemical reaction, but it doesn't matter. All that matters is the initial states and final states when we're talking about delta H. So here's an example. Use enthalpies of formation to calculate the heat of combustion, or I should get with the times and call this enthalpy of combustion for benzene. And the balanced equation is given there. So we're looking at it as per mole of benzene here. So what we need to do is go find a table, like we have a table a couple slides back, right? And we need to be looking for all the things in there. Well, we got benzene, right? We've got CO2, we've got oxygen here, we've got water, gas. So we've got in our table the enthalpies of formation for everything that we need here. So reading off the table for C6H6, we have 82.9 kilojoules per mole. Oxygen was 0 because it's a pure element in its standard state. CO2 gives us negative 393.5 kilojoules per mole. And water gives us negative 241.8. In case you're wondering, I have them written down on my computer screen. I haven't memorized all these values. Although I have memorized lots of numbers you use a lot, like atomic weights for a lot of things you memorize after a while. Like oxygen, carbon, hydrogen, all those ones you memorize pretty quick. Sodium, for some reason, 22.99. Okay, and then what we do is we add up all the values for the products. So on the product side, we have 6 times negative 393.5 kilojoules per mole plus 3 times negative 241.8 kilojoules per mole. That's everything on the product side. And then you subtract the reactant side minus, we have just one C6H6. And that's kind of it, right? Because I guess we have like 7.5 times 0, which is 0. And when you work all this out, you get negative 3086.6 kilojoules per mole. And I guess in terms of sig figs, that's the correct number of sig figs because we're adding and subtracting here, so it goes by the number of places after the decimal. So I think we're all right when it comes to that. And that's it. That will be the enthalpy of combustion for benzene in air. Easy peasy. Doing these is actually pretty quick and routine, and it saves you a lot of time because what we're going to do is look at, if you wanted to measure that value instead of predicting it like we're doing, how you might go about doing that experimentally. There's another method you can use instead of, which is generally more for organic chemistry, I'd say. This is another method for predicting enthalpies of reaction, except the difference here is these are more approximate, I guess I would say. It's using a method called using bond enthalpies. And what we do with the bond enthalpies is we imagine a method of going from reactants to products where we just break every single bond that exists, and then we put all the elements back together to make our product. So we look at the whole reaction as a process of bond breaking to separate it all into atoms, and then reassembly into our product molecules. And this only really works when you're looking at molecules that are covalently bonded. If you have reactants that are like crystals, lattices, like salts, or transition metal, or pure metal, solid, these kinds of things, you can't really use this method for it. Everything has to be bound in discrete covalent bonds, which is generally the case in organic chemistry and biochemistry. So we can define the energy associated with breaking a bond or making a bond if you look at a reaction like this. If you have methane, you have four carbon hydrogen bonds, because the Lewis structure looks like this. And we look at the energy that's required to break any one of these CH bonds. So that's the reaction to homolytically break a bond, which means one of the electrons goes on the hydrogens, one of the electrons goes on the carbon, and we make CH3 plus H2. So this will have an associated energy. It requires energy to break a bond like this. You have to put energy into the system. It's almost always bond dissociation enthalpies are positive values. Because they're endothermic, they require energy for the reaction to go. So in this particular example, to break that CH, the delta H associated with that bond breaking has been measured to be plus 493 kilojoules per mole. If you do the reverse, if you put that bond back together again, you're going to have the exact same value for delta H, just negative. So bond making and bond breaking, same values, just opposite in sign. So somebody went through and tabulated the values for all sort of the common kinds of bonds you would find, at least in organic chemistry. HH, HC, NH, all these bonds that you see here, and put in there the dissociation energies as well. Again, all of these are positive. All of these require energy, and that's because a bond is always lower in energy than the starting molecules. Otherwise, it wouldn't form a bond in the first place. You see there's values for multiple bonds down below as well, single bonds above. One thing I will say, though, is not all bonds are created equal. Like if you look at methane, like we saw before, versus, let's say we're looking at ethene, those CH bonds in these two molecules are not the exact same strength. It's a bit of a difference. So when you see the CH appear in the table, the idea is that we would use this in either case, but we should recognize that that number isn't going to be an exact value. It's going to be sort of an average over a bunch of different types of CH bonds. So in our molecule, the actual strength of that CH bond might be a little higher or might be a little bit lower than that 410 that we plucked out of the table. Some of these values, like HH, you see the little A up there is telling you it's an exact value. Exact values are only possible when there's only one bond of that type that can exist. So HH, you can't make more than one kind of HH bond because there's only one molecule that can have an HH bond, and that's H2. See the same thing for F2, Cl2, Br2. You can't have more than one variation of a Cl-Cl bond. It just doesn't exist. That's true for many of these different bonds. When the two things that are bonded to each other only form one bond, then you can get an exact value. Otherwise, it's an average. So that means that the numbers we calculate, the delta H's we're going to use to get from these tabulated values are going to be somewhat approximate. So what you do is basically you take all of the bond values for your reactants, add them up, subtract from that all the bond dissociation enthalpies for all the bonds in your products. And the value is going to be a rough estimate, at least, of the delta H of reaction. This is a much cruder way of doing it than using enthalpies of formation, but it allows you to do these kinds of calculations on all sorts of new and wonderful molecules that nobody measured enthalpies of formation for. So let's say you come and you work in one of our research labs and you make a new molecule that's never been made before, and you want to know what its enthalpy of combustion is. Well, you can't use enthalpies of formation because nobody measured them. You could measure them yourself, I suppose, but if you don't want to do that and you just want to do it on paper, you can use this method, recognizing that's going to be a little bit approximate. Okay, so let's do this. We have CH4 plus 2O2 goes to CO2 plus H2O. We want to guess, estimate, predict what the enthalpy of combustion for this reaction is. And what we would then do is draw out all of our compounds and draw their Lewis structures and look to see what bonds are present, right? This CH4 has 4 times CH. This one has 2 times OO. Carbon dioxide has 2 times CO. And then water would have 4 times OH. So we would go look up all of those in the table, write those numbers down, and add them up. So here we go. These are the numbers from the table. On the reactant side, those are all the values. We sum them up, and we get this as the total energy required to break all bonds in our starting materials. Then we do the same thing for the products, and what we see here is 3304. So this is just the sum of all the values for those bonds that you find in the table. You take your reactants, subtract from that the products, which, by the way, this is the other way around from heats of formation. Enthalpies of formation, you always take the products, add them up, and subtract the reactants. This is the other way around. You start with your reactants and subtract from that the products. So then you just have your reactant value, have your product value, subtract the products from the reactants, and you get negative 668 kilojoules per mole. This is our estimate using these bond values. The actual experimental value, if you measure the delta H of combustion for methane, works out to be minus 882 kilojoules per mole. So we're off by, I don't know, 150? No, more like 200, 220, 215 kilojoules per mole. So using this method isn't exact. You can see that, you know, it's in the right ballpark, maybe we'll say, but it's not that close to the exact known measured value for this particular reaction. So yeah, it's good. It's easy to apply. It can be applied to any organic molecule as long as you know the structure. Just keep in mind that it's going to bring you to the right neighborhood, but won't drop you off at the right house. So then there's the final method of figuring out what delta H is for a reaction. There's a whole other method that I didn't talk about at all, which is using computational chemistry. We have a course it's a third-year course called quantum mechanics, where we look at the math. People have used sort of first principles from quantum mechanics to be able to calculate for basically any molecule what the heats of formation could be, the enthalpies of formation, what the bond energies are, and what the delta H's of reactions can be. So there's a whole field. There's chemists, thousands of chemists whose whole profession is running computational work on molecular structures. And it takes a lot of computational power. Like if you took a molecule like sucrose and you tried to do a calculation on that, it could take hours and hours and hours of just the computer working away at the calculation that you fed in. The product of all this, and there's different methods and there's always refinements being made, is that for pretty well any chemical reaction now, you can run a simulation and have the computer work out what it predicts the delta H for a reaction to be. So just like we have those tables of values, you can calculate any value that's not on that table, or you can simulate the actual reaction itself. So this is something that you often don't find in first-year textbooks, but really it's the way of it's the modern way of doing things, and it's going to be the way of the future as well. Just because computers are getting faster and faster, and it makes these sorts of calculations easier and easier. So if that appeals to you, like there's many chemists, thousands of chemists out there that never go into a lab because they're not a laboratory-based chemist, they're a computational chemist. So if you like computers and you like chemistry, you can certainly still be a chemist and not have to do any labs. But what fun is that, right? We like labs too. So if you want to actually measure these changes yourself, you might do calorimetry. Calorimetry is a very old classic method to figure out what the energy changes might be in a particular chemical reaction. So we use a device called a calorimeter. You can buy calorimeters that are very advanced and fancy and lots of bells and whistles, and they're very expensive, tens of thousands of dollars. Or you can build your own bargain variation of a calorimeter. Really, all a calorimeter is a container that holds a fixed amount of water where you can do a reaction inside. It should be insulated so that heat doesn't come in from the outside or leave to the outside. So it should be like thermally insulated. And you need to be able to have a thermometer in there and maybe like a stirrer or something like that. If it's a cup like this, you don't even need a stir. You can just swirl it yourself. So the idea in this example, it's just two styrofoam cups, and styrofoam is a pretty good insulator. And so by putting two of them together, I guess you're getting double the wall. So it insulates the inside. What you could do then is pour known amounts of reactants inside, cover it, stick the thermometer in the solution, and then stir it and look to see what the temperature change is as a result. And if you know exactly the quantity of what went in there, the volume of water that's in there, and the temperature change from the thermometer, you can work out what the delta H of reaction was. Calorimeters like this, what we call a coffee cup calorimeter for maybe an obvious reason, they are only really useful for reactions that are done under constant volume conditions, typically aqueous reactions. So if you put in like sulfuric acid and sodium hydroxide and they neutralized each other, that would be great in an apparatus like this. But obviously, if you put like gasoline and you wanted to combust it, that would not work well in a container like that, because it would, first of all, probably melt it or maybe even catch the whole apparatus itself on fire. So we use these if you have like an aqueous solution, typically. A solution-based reaction, like an acid base. Let's look at how we do something like this. Okay, we have a coffee cup calorimeter containing 100 mils of 0.5 molar HCl, and to that is added 100 mils of 0.5 molar NaOH. This is a neutralization between sodium hydroxide and HCl. This causes the temperature of the solution to increase from 21.20 degrees C to 24.56 degrees C. So it's a pretty accurate thermometer to be able to measure that kind of change. Nonetheless, I'm just bringing up my numbers, which I have here somewhere. Yes. So basically what we're assuming here is that all of the heat that is generated from this reaction goes to warming up the water. None of it is lost to the surroundings, and none of it is disappears in any other way. So first of all, what we need to work out is the number of moles that are undergoing the reaction. The reaction looks like this: Na plus OH minus plus H plus Cl minus goes to Na plus Cl minus plus H2O. And these guys are spectator ions, so really it's OH minus plus H plus goes to H2O. So the moles reacting would be, I guess we'll say N equals concentration times volume, which is 0.500 molar times 0.100 liters equals 0.0500 moles. That's how many moles of sodium hydroxide is reacting. It's the same as the number of moles of HCl. So these are matched 1 to 1. And then we calculate delta H. So what we can say is that the Q of the water equals negative Q of the reaction. So in other words, all of the heat that's generated by the reaction is absorbed by the water that it's all dissolved in. The surroundings in this case, it's not outside the calorimeter. The surroundings we're talking about, the water in the calorimeter. The system, I guess, or the reaction would be just the HCl and NaOH alone. So the Q associated with this of the water is going to be equal to, no, it's going to be the Q of the reaction, MC delta T. The mass of the water, if you have 200 milliliters, is going to be 200 grams. The C for water, it's not written here, but we've seen it before, 4.18 joules per kgram. And our delta T is 21.20 going up to 24.56. So that equals 3.36. We'll call it K because delta T is the same in K and degrees C. So that equals 2810 joules, because the grams will cancel and the K's will cancel. So that is the surroundings. That's what they're absorbing. They're absorbing 2810 joules. So the Q of the system, the Q of the reaction, is negative Q of the surroundings. Remember, the surroundings, it's a positive value because it's absorbing energy from the reaction. The reaction itself is losing that energy. So we would just say that's the negative, which is 2810 joules. We know Q is negative when a reaction is exothermic. So if we want to calculate delta H of reaction, that's just equal to Q over N, because typically we express delta H as heat transferred per mole. That equals negative 2810 joules. And we calculated already our moles over here, which is 0.0500 mole which gives us negative 56200 joules per mole, which is equal to negative 56.2 kilojoules per mole. So using this quite simple setup, you can calculate for this reaction, this aqueous-based reaction, what our delta H of that reaction is going to be. Great. If you want to do this for a reaction that's not aqueous, and this is usually the case, you know, like let's say you're doing research on biofuels and you're developing alternatives to gasoline or oil or, you know, furnace oil or whatever it is. And you're using maybe plant-based oils or something like that. An extremely important parameter you need to know is how much heat do you get if you combust this biofuel that you're making. You can't do that in the coffee cup calorimeter because the coffee cup calorimeter would catch on fire. So we have another kind of calorimeter, which we call a bomb calorimeter. And a bomb in chemistry, what that really means, it's a pressurized vessel. It's like where you can do a reaction that's possibly explosive or has big changes in pressure, and it will not break, right? It'll withstand those changes in pressure. So you get a machine that looks something like that. And then what this has inside is sort of a container full of water, and it's the water that's going to be absorbing or absorbing or losing heat. You have a thermometer in there, precision thermometer to tell you exactly what the temperature is going to be. And then inside that we have the bomb, and the bomb, you can see, has a little cup in it. You could put your chemical in there. You then would pressurize that system with oxygen, and then you would have a spark. So those electrodes that you see going in would provide a spark to begin that combustion reaction. There needs to be enough oxygen in there already at the beginning for the reaction to go to completion. And it explodes in there. Nothing breaks. You know, it's under constant volume. That means no work is going to be done, even though that reaction might give off a lot of gas. If it's in a container that can't change shape, then that doesn't do any work. So you don't have to do a work correction. And then the heat, you know, will go into the water. It'll go through the walls there, and then that'll be absorbed. So it gives us our delta T. You know how much compound you put in, so you know number of moles. And if you know how much water is in there, which of course you would know, then you can figure out exactly what the delta H for that reaction might be. Let's do it. 0.783 grams of ethyl ethanoate, which has molecular weight 88.1 grams per mole, is burned in a bomb calorimeter that has a heat capacity C, and this should be a capital C, because these bomb calorimeters have a lot of parts that can absorb heat. So normally what we do is express the entire system with a single value. So the first thing we need to do is figure out moles, right? That's reacting. Grams are great, but, you know, let's call this EE for ethyl ethanoate. The moles of EE is going to be mass over molar mass, 0.783 grams over 88.1 grams per mole. And that gives us 0.00889 moles. I don't know about you folks, but when I start a problem like this, I usually just I pick the low-hanging fruit, something that I know how to do right away. I jump in and I do that first. So that's why maybe figuring out moles might be the best way to go here. What we need to do here is figure out Q. Q of the surroundings, which is the calorimeter itself. The surroundings will be absorbing heat from the reaction. So as a result, Q will be a positive number for the surroundings. That's going to be equal to capital C delta T. Remember, the other version was MCS delta T if you're given it for a pure substance like water. Okay, so we're told that the heat capacity, capital C, is 10.23 kilojoules per K. Times our delta T, which is 1.951 Kelvin. Very accurate thermometer here. And if you work that out, that gives us 19.960 kilojoules. So that's the amount of heat that's absorbed by the surroundings. The amount, the Q of the reaction is just the negative of that because it's losing the energy. So we could say that the Q of reaction is negative 19.960 kilojoules. Calculate the enthalpy of combustion. Well, the enthalpy of combustion then, just the Q reaction over N. N is calculated up above, 0.00889 moles. And that equals negative 2245 kilojoules per mole. Keep your eye when you do these questions on your units. I used kilojoules all throughout here. Just make sure you write them down and stay consistent with it. Great. So that's it. That's the end of this unit. So we're done 5 minutes early. That's not a big deal. We're done chapter 9 and chapter 10. So you can expect the quiz that's going to be opening later today to contain really anything from what we did. Today, I guess we did quite a bit. We learned how to calculate delta H of a reaction a number of ways using either heat enthalpies of formation. We looked at using the bond association energies. We looked at calorimeters, both the coffee cup type and the bomb calorimeter type. And all of these rely on using Hess's law. And they all take advantage of the fact that delta H is a state function. Great. I hope you're all still with me and awake, and hope you all have a great weekend.